Mm. Mhm. Okay. Können Sie mich noch hören?
Noch ist alles gut.
Alles gut. Jetzt schau noch mal rasch in die Einstellungen, ob alles okay ist. Das scheint noch gut zu sein. Sehr gut. Vielleicht ist das die Lösung, dass ich, okay. Right, so we are already recording. Welcome to the lecture. Let's hope that there will be no serious problem this time. So today we want to start with a new chapter, namely localization. So, okay, I need some space. So this is chapter 3. Right. This is chapter 3, is rings and modules of fractions. Rings, modules of fractions. Okay. So it will be the process of localization, and this is one of the most important tools in commutative algebra. So let's start first with the notion of localization of a ring. Localization of rings. And then later on we talk about modules. So what is this all about? I think you all know the notion of the quotient field of an integral domain, I think, right? And what we are going to do now is to generalize this, okay? So everybody knows, I don't have a big audience, but everybody knows the notion of the quotient field, right?
Yes.
I see some nodding, okay. Right, so what, okay. Still, let me write it. Recall construction. Because what we are going to do is almost the same. Construction of quotient field. Of an integral domain. A. Okay, like rational functions starting from the ring of integers. So one defines an equivalence relation. One defines equivalence relation on the set A times A without 0. And we say the following: A comma S is equivalent to B comma D. So two pairs are equivalent. So here A and B are in A, and S and T are non-zero, and also in A. So this is if and only if AT equals BS. Okay, so actually the motivation is, okay, we want to define what this is, this fraction. Okay, how can we do that? Well, the formal procedure is on these pairs, we define the equivalence relation. And then we say that this fraction is defined as the equivalence relation. Okay. So if you want to explain what is 2/3 to your, I don't know, to a kid, maybe you can do it this way, but probably it will not understand. But it's actually what we are doing. This is this. So the idea is here, this equals this. Okay. So the observation is, well, okay. This definition works only if I have an integral domain. So I need, okay, need a integral domain for transitivity. So if you want to prove that this equivalent, this relation is transitive, you will see I need integral domain, otherwise it will not be true. So at first glance, so it may look impossible to generalize this, but one can do it. One can have this notion in more generality by being a little bit more careful here, okay, in this definition. Okay, so if now A is any commutative ring, okay, I carry out the same construction with the small modification. So for this, I need to define what is a multiplicatively closed subset. We call a subset S of A multiplicatively closed. Multiplicative, okay, whatever. Multiplicatively closed. Multiplicatively closed. Okay, if there are two conditions, we want one to be contained in S. The second condition is the closeness under multiplication. So if I have small s and small t in S, then also the product should be in S. That's the definition. Okay, you immediately see if I have an integral domain and S is the set of non-zero elements, then these conditions are satisfied. And the second condition expresses that I have an integral domain. Right. Then define relation on the set of pairs A comma S by. Now it looks almost like above, but there is one change. B comma T. Okay, this is B. Okay, so this is now important. I write here there is some U in S such that, okay, before I had AT minus BS equals 0, but now I say this will be 0 after multiplying with some element from S. So this is the definition now. Okay, so this is a minor modification, and it turns out if I do this, everything works. So there is this lemma that this is an equivalence relation.
And S is now an arbitrary multiplicatively closed set, right?
Yes, yes. S is an arbitrary multiplicatively closed set. Okay, what happened? I don't know what was this. Did you hear the sound? It was a ghost. I don't know what I did. No idea. Okay, maybe let's briefly go through that. It's only the transitivity. So reflexive and symmetric is clear. It's all about, let's check transitivity. Okay, so then, so I assume I have, let's do it. So I have this and this. So assume this equivalence and BT equivalent to, let's say, C comma U. Okay. So the proof is trivial. Okay. So it means there are, in a way, denominators if you want. It's just a question, how do I choose the notation? I call them B and W in S. Now the first condition, here I have B. So this is what I had here. Okay, but here I wrote U, now I write V, it doesn't really matter. And here I write W, BU minus CT, okay. Okay, and then what do I see? Okay, maybe, right. Let me put a long line. Okay, maybe I can put it here. So, okay, B, it's a stupid calculation, VAT UW equals VBS UW. So how did I get this? Well, I just took the equation from above, the first one, multiplied with u and w. Okay, then I go on. But now I reorder the stuff. I think now I write this as B, W, B, U, S, V. And I get this is W. Okay, I will mark in a second so you see what's happening. So what have I done here? So you see V, U, C, T, V, B, U. I think now I have the SV here. Okay, so I took the second equation, multiplied with SV. So this is true. Okay. Okay, and right now we combine it. I pull out the factor TVW AU minus CS. So this comes from the comparison of the first and the last term in this chain of equations. AU CS, okay. And now you see this TVW, this is a product of elements in S, okay? And because S is assumed to be multiplicatively closed, the product TVW is in S, right? So by definition, I see that this pair A comma S is indeed equivalent to the pair C comma W. And I have shown the transitivity. Okay, and this is the lemma. So, right. Good. Okay, so then there is this, we have the notation, or is there a question? Question. The notation, the usual notation, A over S stands for the equivalence class, stands for equivalence class of A comma S. Okay, and the set of equivalence classes is denoted this way. Set of equivalence classes. Or maybe I should have said, I didn't say, so one should always give a motivation. So what is the motivation for this localization? I said it's an important tool, but maybe, okay, what do we do? I mean, this localization probably was first used in number theory, I think. In a way, when you construct the p-adic numbers, this you can see as a localization. But in geometry, somehow, at the I probably will not understand this now, but I say it anyway. These rings, these commutative rings that we consider, in a way, you may think of these are rings of functions defined on some variety. Okay, rings of functions. They have a geometric meaning. Okay, now if you want to study, say, this variety in the neighborhood of a point, you're just interested in local information. You're not interested what happens globally. Then this can be captured by replacing the original ring by another ring, the localization. And that's why it's called localization, because now you kind of look locally what's going on. So this is very much the big idea, okay? Okay, but we can do it in this full generality without ever thinking of this meaning, okay? So this is the motivation. So if you go on, this will become clearer. Okay, when we have Zariski topology, it will become clear that's actually what we're doing. Okay, surely this set is not just a set, but it will be a commutative ring. So we define the ring operations in the obvious way. So put the ring structure on this set. Okay, bye. Now, okay, you tell me what I have to write. AS plus BT. Okay, I define it. What do you think should I write?
AT plus BS over ST.
Right. That's what we do. If you want to have the calculus of fraction, that, and so it will be the definition. And here, obviously, for the product, it's this. I put parentheses to be 100% sure. Now comes the usual routine work. It's completely routine. I mean, it's trivial. Now you have to verify that this is well defined. Okay, well defined. Straightforward, but I will not do it. I mean, it's so boring. But you should do it. Straightforward. Verify. It's always important to know what one has to do. You know, this is kind of nice. Okay, I don't have to do it. I just need to know I would have to do it. And then I do it. It's trivial. It's like, right, clean the bathroom. You don't have to do it. You just know I should have to do it. I should do it. In a way, it's straightforward. Verify that the definitions are independent of the choice of representatives. Okay. Okay, so it's well defined. And then you also check completely straightforward that the ring axioms are satisfied. Verify that the ring axioms are satisfied. Okay, good. So after having done this, okay, this is a ring, commutative ring. Okay, good. So the ring, of course, it must be connected somehow to the original ring, and it is connected by a canonical map. So, okay, the map, okay, okay, we have the ring morphism. In a way, it's a ring morphism. In a way, we would like to have A as a subring, but maybe it's not a subring, so we are careful. So we go from A to this new object, and the element A will be sent to the fraction A over 1. Okay, and then we check again trivial with ring homomorphism. Okay, good. Warning. Okay, we only have to, but there are some trapdoors here. Warning. Trapdoor is, so the warning, F in general is not injective. F in general, not injective. Okay, if you play this game with the integral domain, you construct a field of fractions, then it is injective. Okay, but here no. Let's see what is the kernel. Okay, or see below. See below. Okay, I postpone the discussion. I continue with more other things and do this below. Okay, so so what have we gained? I mean, what is the advantage? I mean, why is this, in what sense could this ring be better than A? Well, we want to have more units, okay? So by construction, you see, S over 1, so S, okay, S is a, I write it again, it's a small s, S over 1 is a unit. It has an inverse. Because, that's right, okay, S over 1. What would be the inverse? Well, it's 1 over S. I can write this, makes sense. I multiply. Okay, by definition, this is S times 1 divided by 1 times S is S times S, S over S, and S over S is the same as 1 over 1. And 1 over 1 is the unit. Okay. Okay. So I gained, so in a way, every element S in the new ring becomes a unit, right? So the remark here appropriate, if A is integral domain, and S is A without 0, okay, this is multiplicatively closed, then this new ring is the field of fraction. Field of fractions of A. Field of fractions of A. Because the same construction. In general, this has a name. Okay, one calls it the localization. One calls S to the -1 the localization. Or ring of fractions. But that's a longer description. Ring of fractions of A with respect to S. Okay, localization. So it's kind of the way I see it. So even if A is an integral domain, okay, it may not be wise to go to the full quotient field. Okay, in a way, I just see it like you have your technical device with some, in German it's ein Schalter. Okay, something you can move, a ruler, you move it, you can adjust. You decide yourself how many units you want to have, okay, or how close do you want to look, okay? You can take the full localization, or maybe you want to take a little bit less, okay? It's kind of allows you to adjust how close do you want to look. So this is a little bit of an intuition I have with this localization technique. Okay, proposition. It's 3-1 in Attia McDonald. You will not be surprised with all these abstract constructions. You see, we did an explicit construction of equivalence classes. But if you say 1/3, would you ever think of 1/3 as an equivalence class? Okay, no. You think of 1/3 of the cake or something like that. Okay, so I think when you deal with fractions, it's only important to know the rules. And here also, and these rules or properties are, given by a universal property. Okay, universe in abstract algebra, always universal property. So this is the universal property of localization. Universal property. So, and it exactly says what it is all about. Okay, so let's assume I have my commutative ring, of course. Then I have another ring B and a morphism from A to B, which I denote by G. Let this be a ring morphism. A ring morphism. Such that, okay, for instance, this G could be the F. Okay, the F I have here, this F. What is nice about this F is that the images of elements in S become units. All of the elements in S become units. Okay. Now let's assume this G has this property such that G, what is it? Okay, G of S is a subset of the group of units of B. Okay. Okay. Elements of S are mapped to units of B. Then there is a unique ring morphism. There is a ring morphism. I hope you can read the ring morphism. H from the localization to B, such that, I mean, let's put the diagram. That's the best way of understanding. Here I have G. So here I put the localization map. This is the F. Okay, and it goes this way. Dot, 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 dot. This is the H. Such that this diagram is commutative. Or I can write it G equals first F, then H. Okay, so every such map which sends S to units factors over the localization. So the localization universal one. Okay, in a way, if you have the if you understand the localization, you understand all those maps. Okay, and the proof again. It's very easy. It reminds me of a course I had in Zurich on commutative algebra. Okay, by a professor, a specialist, Markus Brotmann, specialist in commutative algebra. Actually, the course was on algebraic geometry, the title of the course. And then he said at some moment, well, this, what I'm doing here, this is nothing, it's just calculus of fractions. And if you think about it, it's true. It's just calculus of fractions. That's what we're doing, calculus of fractions, okay? Because there is no, well, plus, minus, times, we divide. Okay, when we go on, maybe later on, we have also a notion of topology or Zariski topology, so it's a bit more sophisticated then, but basically that's what it is, okay? Calculus of fractions. So, proof of the proposition. First, let's talk about uniqueness. But by the way, calculus of fraction is not that easy, okay? You know, in school, it's sometimes difficult, yeah? And even at university, you find many students, they don't know how to do it. Maybe not in mathematics, but in other disciplines. Uniqueness. So assume we have H as in the diagram, have H as in diagram. Okay, so I want to show uniqueness. So what is H of A divided by 1? So this is H of F of A. But first F, then H is G. So this is G of A. So we see this is for A in the ring. Okay, good. In particular, so if I, okay, now I replace A by S. So H of S divided by 1 is G of S. For S in my multiplicatively closed set. Okay, so then, right. Okay, I'm going very slowly. Why not? Right. So what is H of 1 over S? Okay, one shouldn't go. What is this? We know 1 over S is S over 1 inverse. I noted it before. Okay. Right. Because H is a ring homomorphism, it transports, you know, inverses to inverses. So this is this. Maybe let's go very slowly, super slowly. But I notice this is G of S, so I get this. And it makes sense, right? It makes sense. Yeah, I assumed this property. So I assumed this. So this is in fact, yeah. Good. So okay, now one more step. So H of A over S must be, okay, let's go very slowly. This is A over 1 times 1 over S. I combine what I said before. Okay, it's, oh my God, let me write everything. It's a ring homomorphism. And then I plug in what I know and I get this. It's G of A times G of S to the minus 1. So I mean, the upshot is H is completely determined by G. So if there is such an H, he must be unique. Okay, must be unique. So existence, so this was uniqueness, now existence. You see, this proof, actually, you just need to know the whole, okay, how do you say? How do we approach these things? And then you can prove everything yourselves. Okay, I just tell you. So in a way, I just tell you how to speak. But then, right, exists. So what now? now I need to show the existence. I just define H using this yellow relation. So I define, okay, I say H of A over S. This should be this. But then, of course, I have to show, well, first of all, this makes sense. Note, GS is a unit. So this makes sense. I mean, this expression here is defined, and I have to show well-definedness. Maybe I can do it. H is well-defined. Okay, maybe let me do it because it's quite essential. So let's say I have A over S and other representation A prime over S prime. Of course, the S are in the capital S. So this means there is some T in S with the property T times AS prime minus A prime S equals 0. Okay, good. So I have this relation. This is a relation, polynomial identity in the ring A. I map now with G. Okay, I map with the G. Then I have, it's a homomorphism. Then I have this. Okay, 0 goes to 0, right? Then I note that the G of T is a unit. So since this is a unit, I can multiply with the inverse, and I remove this guy here. Okay, here has an inverse. So I'm left with this equals 0. Okay, and then I use, right, that this and this also have inverses. Okay, and I arrive. Okay, now I don't. Okay, I don't write all the steps. I get this. So I see this was actually, this is good. This is well defined. H is well defined. And now it's trivial check. Okay, it's that kind of clear. H is ring morphism. Okay, and I'm done. Okay. Do you have questions on that? I mean, what can I say? I mean, I say the proofs in a way are trivial verifications, but the concept is non-trivial. I mean, it's not clear that, I mean, I have to check that I made the right definition so that everything works. Okay, someone has to do it. Okay, so properties of the localization.
Yeah, I don't understand something. We said that F is in general not injective, F that connects our A with our localization.
Yes.
But then we said that everything is invertible, isn't it?
No, I didn't say everything. The non-injectiveness I will discuss in a moment. But I don't say everything is invertible. This is not true. The only thing what I say is the G of S. This is invertible. But this is my assumption.
Yes, but we always use one by divided by S as if
this is invertible in the localization. Because, okay, I show you again.
But I mean, if it is not injective, then
yes,
it could be that some S is mapped to 0. And then
no. Oh, okay. Let's check. This is, I don't think this is possible. Like, okay, good question.
I think the problem is that you can only take any element of S if you want to have invertibility. So the small s should be in capital S.
Yeah, I think, but maybe this is.
okay.
But you said S, what did you say? S, that this could be 0 or what? Or
That
or what?
That this could be mapped.
Let's see, can this happen? 0 is 0 over 1. So this would mean there is some T in S, okay, such that S times 1 minus 1 times 0. No, I'm very pedantic, is this. So what I get, this means TS equals 0.
Again.
Okay.
I mean, we don't have any
but then I see 0 is in S. Did I exclude it? No.
No.
This is okay, because the 0 ring is a legal ring. Okay, so if my multiplicatively closed set happens to contain the 0, I can do the localization and I get the 0 ring. Everything is fine. This is okay. This is okay. And I even want to, I don't want to exclude it. Okay, this is something that I want to allow. Right.
So as soon as 0 is in it, we get the 0
right.
ring.
So this phenomenon that you observed happens if and only if 0 is in S. It's kind of somebody wants to divide by 0. And then I say, okay, you can divide by 0, but only if the thing is 0. Okay, then 0 is 1, and then it's, everything is good.
Yeah.
But I allow this, but then only in the 0 ring. Okay. Good question. Very good question, actually. So properties of the localization. Okay, I see the localization actually as this ring morphism, A going to this ring. Let me write again what it is. Okay. So property 1. So just I summarize, I mean, what I know. When S is in S, then f of S is a unit. Of the new ring. 2, and this is very interesting. This is the kernel of F. Okay, this is, what is the kernel? Well, I know. This is the set of A that are mapped to 0. What does it mean? That A over 1 becomes 0 over 1. By definition, it means there is some S with the property S of A equals 0. Because this exactly means, okay, if you, I can maybe, I think we just had it. This means there is some S in S such that S times, yeah, A times 1 minus 1 times 0 equals 0. So it means by S equals 0. It's exactly that. So the kernel of F consists of those ring elements A that are killed by multiplication with an element of S. Okay, those are become. Right. So I'm not going to give a geometric interpretation. There is one, but I'm not going to give it now because somehow. Just let me write it in a more formal way. This is the union over all S in big S of the annihilators of S. So annihilator of S are the set of A such that SA equals 0. So it's a union of annihilators. Okay. 3. Right. How? Okay. We are not, this somehow is not complete, this description. In a way, we want to have the smallest string having this property. And so this I express by saying every element of this localization ring is of the form FA times FS inverse for some A in A, S in S. And we know all these properties hold, I think, by construction. Okay, now easy to see that, I mean, localization I can characterize with the universal property, but I can also characterize it by this property. Easy. Okay, localization is characterized by 1, 2, 3. I think this is in Atiyah Mac. If you want to check it, Atiyah McDonald corollary 3-2. Probably it has a proof. I don't know. But the proof would be trivial. Okay. Okay, so I want to give an example. Or maybe one remark that's very important, but we know it already. If A is an integral domain, then F is injective. Because if we look at the kernel of F, here is the kernel. So if you have SA equals 0 and S cannot be 0. Okay, if S would be 0, right, then, well, A must be 0. Check for yourself. Small s cannot be 0. And then since I have an integral domain, I conclude A is 0. So good. I think maybe a main difficulty when you operate with localization is that the F is not injective. Okay. It's like before we had this tensor product and this thing, you know, you can lose injectivity. You know, this is a property, and here you also have it. But you should think of it also as a bonus. I mean, it also increases your flexibility in operating with this. It's not just bad, it's also good. But because then you can kill things in a way, unwanted things. So I give one example of a localization where this happens. So let's say, and you see, it's not completely abstract. So I look at the product A of two rings. A is A1 times A2, it's a Cartesian product. And I assume A1 is an integral domain. Okay, so I kind of want to kill A2. I want to gather, okay, remove it in a way using localization. This I can do by choosing the following multiplicatively closed set S. So it's the set of, okay. How do I write? Maybe I write, let me write it differently. Maybe I write it this way. A1 without 0 times A2. This is multiplicatively closed. And it's multiplicatively closed since A1 is an integral domain. Okay, so these are my set of denominators, if you want. All of these elements in my new ring should become units. Okay, they should become units. The question is, what is this localization? Can I describe it in simpler terms? And I can, so let's do it. So let F denote the localization. Denote the B, the localization. Okay, I can find out what it is. Most importantly, what is the kernel of F? Now let's write what is the kernel. Okay, so what is the kernel? What do you think? What will be the kernel? These are, okay, let's go back here. Here was the kernel. Those elements now in the product, A1 times I2, that are killed, okay, become 0 after multiplying with an element of S.
Yeah, so I think it's 0 comma any element.
Very good. Very good. 0, okay. 0 comma A2. So I use suggestive notation, A2, any element in capital A2. Maybe as an explanation, maybe note. Okay. So why is 0 comma A2 in the kernel? Well, I take the element 1 comma 0. 1 comma 0 is a legal element of S. And if I multiply, what I get is 0, 0. So this is basically the proof. Okay. Okay. I can kill the second factor. Oh, sorry, I can kill the first. What do I say? Yeah. I think I kill the second factor by this observation because I can multiply with elements of the form 1, 0. And the 0 in the second factor kills everything. Okay, so let's go on. So what do I have? So here, so I put, on the one hand, I have f horizontally. This is my localization map, which I want to understand, but it's defined abstractly, but I want to understand it more concretely. Now I suggest, okay, let's put here just the projection map. Projection onto the first coordinates. And now, right, what did I say? I claim now I can factor. I have a ring homomorphism here. Let's call it F twiddle. I mean, for that, I need to check. Yes. I need to check that. Oh, no, sorry. No, I was confused. I wanted to use the universal property. No, this is directly clear. So let me write it. F twiddle of A1 is defined as F of A1, 0. Okay, so basically this is basically the restriction of F. So I have this commutative diagram. And I note that the F twiddle is injective. Yeah. So there is something, right? Yes, I think it's injective because I've kind of removed this kernel. Okay, now I strict to A1. If I intersect here with this A1 seen as a subring of capital A, I get 0. Okay. So every element, now let's see, let's see. Every element, okay, F tilde is injective. Is it surjective? Well, not quite. Every element of the localization is of the form F A1, actually I can put twiddle, F twiddle of AS1 to the minus 1 for A1 S1. A1 S1 0. This is right. This follows from, I mean, we have this general property. This is for the localization, this is the property 3. Now we apply it to our S, this S, you see? And right. Okay. So, and once you know this step, maybe you need to think a little bit to verify. It follows that our localization is actually the quotient field of A1 is quotient field of A1. Okay. A question on that or? No question. I think it's a good example where one can see, okay, what the localization does in a concrete example. Okay. No question. Ah, okay. I'm left with 2 listeners. Okay. So how do we get these multiplicatively closed sets? Next topic is whenever I have a prime ideal, I can get such a set. So this is localization of the prime ideal. A prime ideal. Localization of the prime ideal. So let's assume I have a prime ideal. Let P be a prime ideal of A. Okay, then let's take the complement. S I define as A minus, as a set theoretic difference, A minus the prime ideal. This is multiplicatively closed. This is the definition of P being prime. The product of two elements not in P is not in P. That's what defines prime ideal. So actually I can say this is, maybe I could even make it nicer. Let's see, let's assume P is an ideal. Then I can say this is multiplicatively closed if and only if P is a prime ideal. So this is a one-to-one characterization. So I can form the localization with respect to this set S of denominators, and it has a notation. The notation is this: A index P. So this is this. Okay. This is the name for this localization. Localization at the prime P, or more concretely, okay, I want to write it in terms of fractions. This is this collection of fractions. I write this way. A comma S are in A, but S is not in P. Okay, so intuitively, I mean, once I form, if you look at this just formally, you have this collection of formal fractions. Okay, and you can take any fractions where the S denominator is not in P. So you must not divide by an element of P, but you can divide by any elements outside of P. Okay, that's what this is. Now this ring is kind of a beautiful ring. So what are the best rings? The best rings, probably the best rings are fields and fields. And then after the fields, I think probably the local rings in a way, right? I mean, if you want to keep some, maybe it's not quite true. You can also say rings of dimension 1, but the local rings definitely are, okay, we can understand better. And this is a local ring. AP is a local ring. A local ring. Okay, with maximal ideal. What is the maximal ideal? Local ring means there is exactly one maximal ideal. So here it is. Let's denote it M. So it consists of those quotients A over S, where now A is in the prime ideal and S, of course, is outside. Okay, so I think we should prove that. Okay. So proof. Okay, first, there are a couple of things to check. So I would say it's clear that M is an ideal, hopefully clear. I say clear. What do you check in your mind? M is ideal of AP. Okay, close. Okay, sorry. I mean, you think of what happens. Say, for instance, why it's multiplicatively closed. Okay, you have A over S. You multiply with anything. I don't know, B over T. Then you have AB over ST. And you see the AB, I mean, AB will be in P because A is in P. and P is an ideal, right, for instance. And then for the sum, same business, etc. So this is trivial. So now I want to show that this is a local ring. So the question, actually, I have this M. And then what I want to show is that the complement of M, I mean, consists of units. So let's do that. Suppose I have an element B over T, my localization, which is not in M. I want to show it's a unit. Okay, so then, okay, then let's be careful, okay, because we have to be careful because of the non-injectivity of F. Then I say B cannot be in the prime ideal, clearly. Otherwise, I will be in M. So if B is not in the prime ideal, it means B is in S, because S is the complement of P. So, okay. So how do I get the unit? Well, now I can write B, okay. Sorry, I can do this the other way around. I can write T over B because I can divide by B. This is a legal element in AP. Okay. T, what did I say? Where is, of course, I mean, right. B is in S and the T is in P. And why is it in P? What did I say? Sorry, T is okay. Now confused briefly. Sorry, now nothing to show. Everything is okay. I was just confused. Okay, now let's see why it's a unit. Now, so I have B over T times T over B is BT over TB, and this is 1 over 1. This is, okay, this is the one. I mean, I can call it, you understand, this is the one of the localization. So maybe I should not write this. Maybe it's 1 over 1. So it follows B over T is unit in the localization. It's a unit here. Okay. So I have this ideal. Every element outside the ideal is a unit. So I'm done. Maybe except one thing one should, okay, a local ring, it should not be 0. So the claim is, let's check this as well. 1 over 1 is not in M. Okay, let's also do that. Okay, so in a definition of a local ring, exactly one maximal ideal. It should not be the 0 ring. So let's check this. Okay, so otherwise, maybe in parentheses. Okay. If 1 over 1 would be in M, we would have this form, A over S. Okay, and A would be in the prime ideal. So I would have, okay, let me write it. S over 1 would be the same as A over 1, and I would have, there would be some T in S, such that TS equals TA. And then it would follow, let me see, TA. Okay, the TS is in S. Okay, this is in S. So the TA is in S, so this is not in P. And then it follows that A is not in P. Okay, and this is a contradiction. I mean, because if I assume I have this in M, actually, no, I wanted to assume A is in P. So this is all good. Now, okay, I apply now to conclude this proposition 116 at Tia McDonald, which gives me that AP is low, gives the assertion. So, okay, maybe an AP local ring with maximal ideal M. So this is the complete proof. Okay. What else? Yes, let's give some examples. Or is there a question to that? No question. So we call this localization at the prime P. Here is one example. This is the number theoretic example. Probably was the first example that was considered in this situation. So the ring is the ring of integers, and the prime ideal is a principal ideal generated by a prime. P is a prime number. Okay, now I do, okay, localize. I have my ring, and here I write, okay, maybe let's do this in color. Okay. You see, I localize at the prime ideal. Okay, you should not write, if you write this, it's not so good, it's not good, because this usually is the notation for the p-adic numbers, okay? Right, so I don't write it this way, I write it this way. So this is the set of quotients, m over n. M and n are integers. And, okay, p should not divide n. Okay, the n is outside of the prime ideal. Now you see, you can view this, I mean, this m over n here, I mean, you can think of this as a subring of Q. Okay, so you can say, okay, this is perfectly fine. On the one hand, we have the abstract construction, but now very easy, you check. This is, and you can, in a canonical way, can view as a subring of Q. Okay.
What's there? P plus n, P unequal n, P.
P is not, does not divide.
Okay, yeah.
Not divisible. Not divisible. So it means n is not here. Okay. Thank you. Right. Okay. So maybe not now. So this is ring. And in number theory, okay, you can form the completion. I don't know. I just say it. It's possible to form a completion with respect to the p-adic valuation. And then what you get is this ring of p-adic numbers. Okay. It's very closely related. This is just a side comment. Okay, another example, polynomial rings. A is a polynomial ring over a field K. Let's assume K is infinite. Okay. Right, because I want to give a geometric explanation. Okay. Xi are variables. Okay. P is a prime ideal in the polynomial ring. Prime ideal. Okay. Okay, I try to give a geometric interpretation of the localization. So I look at the zero set of my prime ideal, which is an algebraic variety. Let's denote it V. It's a set of points. This is now a small x in k to the n. Think of k as the complex numbers, okay? Algebraically closed. Agreed. Or if you want real numbers, is also okay. Set of x such that for all f in the prime ideal P, f of x equals 0. So this is the algebraic variety. So I think it was treated in the exercises, algebraic variety defined by P, algebraic variety. So this is kind of the geometric picture of this prime ideal. if you want. It's a geometric object. So now what is the localization? The localization consists of certain rational functions. You see here, A is an integral domain. So now so this localization, A localized with respect to P is a subring of the field of fractions. Okay. So the field of fractions I can view as functions. They are just not defined everywhere. Now, which rational functions are in this localization? Okay, let me write this or explain this. Then A over P localization consists of the rational functions. So that's called G over S. Okay, which are defined. Okay, let me first finish the sentence and then explain. Which are defined. So this function, right, I want to be defined on V. Okay, but actually I write which are defined at Zariski almost all points of V. So if you want to fully understand this example, you need to, there needs some background in basic algebraic geometry, but I think it was explained in the exercises. So it is called, this is for the geometric intuition, the local ring of k to the n. Now here's the geometric object, the affine n-dimensional space along the variety. Okay. So okay, use example. You may think of, okay, you could have like, for instance, V, okay, here is the simplest example. V is a point. What is a good name for the point? I don't know. Maybe 0. I know 0 is a point. Okay, here. Here, okay, maybe K2. So I want to illustrate a little bit. So concretely, I take K2. Think of the plane. In the plane, you take the point 0. 0, okay, this 0 set of the maximal ideal. Okay, the prime ideal here would be the ideal generated by the two coordinate variables x1 and x2. So the localization consists of those, okay, functions, G over S. G and S are polynomials. You can write them. Okay. No space. Huh? I move it over there. Polynomials. And important is S evaluated at 0. I write 0, 0. Okay. Is not 0. So this expresses here S is not contained in this ideal. Okay, so it's the quotient of two polynomials, G over S, but S must not vanish at 0. So in particular, the function is defined at that point, at 0, okay? It's the functions, rational functions that are defined here at the origin. And okay, if I can go on, maybe with another, okay, maybe I should have, right, now let me do this. Now I move this down. Okay, so. is something I don't know where algebra. Okay. So, or another example. Okay, example 2. K2. Now let's assume the zero set is not a point, it's a curve. I don't know. It can be like this. Is a curve. It's a curve. Okay, I could write. I don't know. This is not a very good example. Maybe I take the prime ideal is this. It's this school example parabola x2 minus x1 squared. Okay, so this is not a very nice picture, but okay. So then your localization will consist of the functions g over s. Okay, g and s, again, polynomials. And s, okay, s is not in P. And what does it mean? If you restrict it to V as a function, it's not a zero function. So it means S is not in P. So you see this function G over S. Okay, it may be, okay, I give you an example. I mean, I could have, okay, it's okay if this function has zeros on B, but it must not vanish on B. So for instance, I could have 1 over, now I take, okay, what do I take? X1. So this is here. Because X1 doesn't vanish completely on B. Okay, but on this point it vanishes, but this doesn't matter. So what I wanted to say, this localization, and I put here these local rings, this is the prototype of local rings arising in algebraic geometry. Prototype of local rings arising in algebraic geometry. Okay, so all of the examples are of this kind. And hopefully you can see now a little bit of the geometric nature of the localization, a little bit. In a way here, okay, I know this is hard, but in a way here, you only want to understand in this example what's happening. Okay, somehow. I want to understand what's happening in the neighborhood of the origin. And here you only want to understand what's happening in the neighborhood of the curve, in a way. This is the intuition behind. Okay, and this may be hard to formalize, one would think, but using algebra, you can do it in this very clean and elegant form. Okay, are there questions on this? Or it may appear that when I do the algebra, I'm rigorous and it's exact, but it's just abstract. And whenever I try to explain what the geometry was behind, then it may sound reasonable, but it's unclear. It's kind of right. No comments. Even Lev doesn't say anything. Okay, I don't know whether that's a good sign.
I think I should keep my questions until the end.
Maybe it's not a good sign. If people are completely quiet, it means they are.
Okay. I just think that I should keep my questions now until the end of.
Oh, very good question. Very, very good. Then let's go on. I have another 10 minutes. Oh, okay. I have one remark, but this is actually was answered. This was your question. Let me put it anyway for the record. The localization can be 0, but this happens if and only if 1 over 1 equals 0 over 1. And this is if and the case if and only if, okay, I write it here as an S in S, such that S equals 0. And this is the case if and only if 0 is in S. Okay, so I said it already, but I think for the record. Okay, so localization, there are two classes of examples. One big class is the one I just discussed. It's the localization of the prime ideal. Okay, so here, whenever I have a prime ideal, I get a localization. But there is another class equally important. This is the localization at powers of f. At powers of an element, at powers, let's say, of f, whatever is f. Okay, so the point is, so let abstract situation commutative A, f an element of A, and for S, I take the set of powers of f. So set of f to the n is a natural number. Okay, then S is multiplicatively closed. It's fine because 1, f to the 0 by definition is 1, and clearly it's closed on the multiplication. Okay, so I have a localization. Notation. Okay, this is AF. Let me put here. So this is the localization. So this formal consists of these formal elements G divided by some power of F. G in A and natural number. And important not to confuse. Right, should I say this now? Maybe not now. Yeah, this is the localization of powers of F. So don't confuse. With, you see, I could also write A, and now I could write, okay, with, okay, maybe in red, or what is good, orange, with parentheses. Okay. This is defined if the ideal generated by F is a prime ideal, which is defined when F is prime ideal. Okay, so you really have to distinguish, okay? If you remember, when we form this, we have the quotients, and in the denominator should not be in the ideal generated by F. So the F does not divide the denominator. However, here, the denominators are just the powers of F. This is a completely opposite situation, but notationally a bit close. So everyone has to be careful. Okay, so examples are always good. Take the polynomial ring in one variable over a field. Okay, so I explain now these two things. Maybe I go to the next page. Don't have to save any space. So the element, okay, f is x, okay, f is x. It's, okay. So on the one hand, I look at the prime ideal, this guy, the prime ideal. I localize with respect to the prime ideal, get a set of quotients, f over g, f and g polynomials, in one variable, but g evaluated at 0 is non-zero, okay, which means g is not in the ideal, so it means, maybe I can write again, means g not here. Okay. On the other hand, now I can localize with respect to the powers of x. This is this, consists of those elements, f divided by some power of x. It's not the same. Okay, completely different. Okay, right. Question or I think this would be a good moment to stop. Next time we will discuss, we will discuss the localization of modules, okay? And at the beginning, it will be basically the same. And then what we will also investigate the connection of to the tensor product and so. So localization of modules, tensor product, kind of this is a very happy marriage in a way. It's very harmonic. You have very nice properties. Okay, so I suggest that I stop now the recording.